Welcome everyone. Welcome to the second event in our Cool Insight webinar series. You have the option to hear this webinar in English or in French. If you check the bottom of your screen, you should see the globe symbol, where you can choose to either hear the original in English or select the live interpretation in French. Before we get started, I would like to mention that this session will be recorded. So please keep your microphone on mute unless you're asking a question towards the end. If you experience any technical difficulty or are unable to see the slides, please let us know in the chat and we'll try to fix it. If you have any questions during the presentation for the speakers, please write them in the Q&A section. We will try to answer them as we get along. In any case, there will be plenty of time for questions at the end. I was supposed to hand over now to Suir Amami, but unfortunately she's not available. So I will be introducing today's webinar. So this is the second in our Cool Insights webinar series brought to you by the International Institute of Refrigeration and the Efficiency for Access Coalition. So the International Institute of Refrigeration, or IIR, is an intergovernmental organization fostering collaboration and enhancing knowledge on all aspects of refrigeration and heat pump technologies, as well as their applications, to contribute to a sustainable future for all. The IIR sees walk-in cold rooms as an important topic to help increase food security through reducing food waste, enabling farming and food businesses to sustain the quality and nutrition of produce they sell. The IIR produced a guide to help buyers and businesses make choices on cooling equipment that are right for their situation. Today's session builds upon the first webinar. The recording is available. And today will be a more technical and a deeper dive into decisions on sizing of the cooling equipment and power supply, the key performance parameters, and some important technical questions that buyers and suppliers should be discussing with each other when specifying and selecting walk-in cold room equipment. It is a technical information because the choices are complex and it's important to get them right. So you can see on the slide today's program. The practitioner's technical guide was prepared by a diverse team of over 30 experts from around the world, led by the IIR and Efficiency for Access with support from World Bank. The guide is available free of charge on the IIR website. The main guide has over 200 pages of technical and practical advice for project managers, specifiers, users, and others. And there's also a shorter overview of 28 pages of key points that is available in both French and English, and both are available for download free of charge on the IIR website. So today, in today's webinar, we will focus on small walk-in cold rooms because just over 30% of the world's population relies on rural and traditional food systems, with most of them in Africa and Asia. The FAO has recommended that small-scale technologies should be prioritized as this maximizes market flexibility and co-benefits to communities, supporting more operators in the local economy. On the slides, you can see the main types of walk-in cold rooms that will be covered: pre-assembled, flat-packed kits, self-built, reefers, converted containers, and so on. The guide advises on power supply system choices, whether grid is connected, off-grid, or hybrid solutions in rural, urban, or peri-urban global south locations. The focus of the guide for the walk-in cold rooms is primarily on perishable fruits, vegetables, and similar produce. So today's speakers, we'll hear today from several of the experts who helped prepare the guide. Today's speakers will include Giovanni Cortella. So Giovanni is a professor of thermodynamics and refrigeration at the University of Udine in Italy. He was president of the Commission D1 refrigerated storage of the IIR. His expertise is mainly on cooling systems with a focus on the improvement of energy efficiency of plants and on heat recovery, aiming at fighting emissions of greenhouse gases. We will also hear from Jeremy Tate. Jeremy Tate is a mechanical engineer and independent policy specialist for sustainability and energy efficiency of electrical appliances and equipment. He has over 25 years experience working with governments, national and international agencies, and business on technical policy and compliances. He has led and supported development of energy efficient policies and test methods for refrigeration and cooling equipment, HVAC, electric motors, distribution transformers, and virtually all types of domestic appliances in many parts of the world, including the EU, Egypt, Pakistan, and for the African Union Commission. Since 2018, Jeremy has increasingly applied his experience to supporting energy access work in global South economies, establishing quality frameworks for appliances used off-grid and with unreliable public grid. Jeremy jointly led conceptual development of the practitioner's technical guide on working cool rooms for rural and off-grid use in global South economies with the International Institute of Refrigeration. We will also hear from Bas Hetterscheid of Wageningen University and research in the Netherlands, as well as from Victor Torres of Solar Cooling Engineering in Germany. Victor Torres is the founder of Solar Cooling Engineering, a consultancy company in the field of sustainable solar cooling solutions with focus on local manufacturing. Victor holds a degree in mechanical engineering, a master's on air conditioning technologies, and a PhD in design of solar cooling systems. He has over 20 years experience in the industry, academia, and international cooperation with specialization on solar cooling solutions, such as cold rooms, milk tanks, and ice makers. So I will now hand over to Giovanni Cortella for the first part of this webinar.
Thank you very much, Monique, for your nice presentation. Okay. Do you want me? I can ask for control so I can move the slides. Well, now let's start with this slide. It says, a roadmap to a successful working cold room project. So what's the key to a successful cold room project? And this is the question which drove us when we were preparing the table of contents of this guide. And whether you're talking about small or large cold rooms in moderate or severe weather conditions, for a good design, a holistic approach is needed, starting with a thorough planning supported by data analysis and policy and regulations from the governments. Like, for example, national cooling and action plans. In an environment where people are aware of the benefits of using a cold storage, so you have to train farmers and market owners, where cutting-edge technology is employed to improve effectiveness and reliability of the systems, so you have to train designers and technicians, where partnerships and links are established among the farmers, where stakeholders and with the stakeholders and all actors, and finally, where access to financing and state-of-the-art appliances is made easier. So that's the reason why we are talking about a holistic approach, and that's the reason why we were moving to a process which is here in this slide. And this is the ideal path that the guide aims to describe. It can be schematized in a flow chart. This flow chart you can, oops, something went wrong where. Monique, maybe you had better drive the slides because there's a delay when I move them. So please, can you go back one slide? Thank you so much. You better control it. So we were saying this is the ideal path that the guide aims to describe, and it can be schematized in a flow chart. This flow chart follows in some way the contents of the book. The aim is to offer guidance through the steps to plan, specify, install, and run a cold room, enabling effective discussion with specialists, suppliers, and funders. So specifications for a cold room are not easy to define, and this integration of the cold room into a value chain is quite complex as well. and possibly it needs independent and professional advice, better if found locally, because you have to consider specific requirements of the area or the market. So the path from the first idea to an operational cold room is shown here. First, you have to check if a cold room is the right solution to the problem. And through the evaluation of the market needs and the availability of technologies and funding. This is a crucial point. A cold room is expensive. Its correct operation is not trivial. Possibly other solution can be found to extend the harvest season, for example, and could be the answer to the problem. Provided the cold room is the right choice, then cooling loads are to be estimated, depending also on the purpose of the cold room. For example, if pre-cooling is considered, ideally a dedicated system should be used to reduce the pre-cooling time. So based on this information, the size and the type of the cold room is chosen together with the refrigerating system to ensure the cold room can be effective and afford its duty. Then the electrical power requirement is estimated. And once the site is chosen, the available power supply is known, and so proper configurations for the solar photovoltaic production can be suggested, together with some effective energy storage solutions to afford unreliable or even off-grid operation. In this guide, we decided not to consider fuel power generators because of their serious drawbacks, high maintenance costs, fuel costs, and also negative environmental impact. On the contrary, among the renewable energy sources, photovoltaic has been considered as the most important choice, and so has been considered in this guide. Business models are then compared for the best exploitation of the investment. Now we are at point 6. In fact, revenues generated might not be sufficient to cover the high investment costs or be affordable to the customers, such as smallholder farmers. So innovative business models are proposed in the guide, for example, service-based models. The most promising value chains are to be identified. Reliable market access has to be ensured for logistics and for operations. Finally, the business model should guarantee the highest utilization rate for the cold room. Financing route must be identified, risks and costs must be well known and correctly evaluated. At this point, we are at point 8 in this flowchart. Technical specifications can be outlined and the go, no-go decision stage is reached. So we have to decide. And if the decision is to proceed, the tender procurement process starts, and then we move to installation and commissioning. Installation is a crucial phase as well, because a good installation prevents from unexpected failures in the future and allows for a long lifetime of the system. And commissioning is important as well for the same reasons. So during its lifetime, then the system has to be operated, maintained, managed, and this is the last step in the guide towards a walk-in cold room fully operational. The next, please. So we can see from parts 2 to 5, we have the plant sizing process, which is one of the topics, I would say, of this seminar. And while in this slide, you can see how in the contents we deal with the process of planning a cold room. You can see in the English language on the left, in French language on the right, how the planning process has been dealt in part 3 of the guide. We don't have time to go too much into detail among the various phases in this flowchart, but it's important for us to show you how much detailed is the discussion of these topics in the guide. And in the next slide, we can see also what happens when we deal with sizing of the cold room and this cooling system. The next slide, please, Monique. Thank you. As well as estimating the electrical power demand and the power supply options described in part 5. So In the next slide, we will see what will be the topic of the next speakers. They will cover the path from the cooling to the power supply. And first of all, we will have to discuss the importance of pre-cooling, thus posing the question if the plant aims to cover also pre-cooling needs before it is correctly designed. A cold room designed for pre-cooling will be able to supply also cold storage if it's needed, while a cold room designed for storage will definitely fail when warm produce will be loaded. So that's a very important choice. Once size, temperature, relative humidity, air velocity are defined, then they can be the input for the assessment of the thermal loads. A defined average outdoor operating conditions, thus estimating the cooling demand with the unit as the supply. And so the third step is the choice of the components of the plant to allow the assessment of the profile for the electrical power needs. So from the cooling demand, for the cooling demand profile, we go to the electrical power profile. And this electrical power need should ideally match the energy availability. However, solar energy prevents from having energy availability 24 hours a day. And thus, this requires some kind of energy storage, which can be electrical or thermal storage, and we will deal with both of them. So this is the agenda for today. I don't want to steal more time to the next speakers, so I would like to leave the floor to Sebastian Atteshade, who will deal with the first step, and then he will hand over to Jeremy Tite and then Victor Torres. Thank you. Please,
thank you, Giovanni. Yes, I will be talking about cooling and the purpose of cooling and cold rooms. Let me see if I can go through slides. Yes, there I go. First, I want to take a step back. Why are we cooling? And why is cooling so effective? And basically, what little people or what not many people know is that fruits and vegetables are alive. So when they get off the tree or from the ground, they're still alive and they are breathing, releasing heat. They dehydrate, they can be hurt if you drop them. They can get sick from diseases and they can die when we throw them away. And this process of being alive can be influenced by regulating the temperature, relative humidity, and airspeed around the product, meaning that we can control how long fruits and vegetables can be living in this process. So that is actually where or why cooling and relative humidity and airspeed are so important. And that's also depicted in this picture where we show the control measures in green as well. Knowing that the products can be influenced, we want to kind of know how they can be influenced. And that is elaborated quite nicely on page 26 of the guide being presented. Because in the guide, we elaborate the impact of temperature on products. For example, you see in the top table that respiration, so the breathing speed, can be regulated by temperature. And the lower you put the temperature, the lower the respiration, the slower the deterioration of the product. So basically in this overview, you can see everything in green has a positive impact. Everything in red has a negative impact on the shelf life of the product. And what you can see as well, for example, with temperature, is that chilling injuries can occur. If you make products too cool, they can turn brown. For example, if you store a banana at 5 degrees, it will turn brown because it gets chilling injuries. So there's a balance we need to strike between temperature, relative humidity, and the airspeed when designing walk-in cold rooms. Yeah. Let me see, next slide. Yeah, there we go. And now now that we know that cooling is so important and relative humidity and the others, I want to guide you through a little story, and that story is about roses being transported from the Netherlands to Germany. And basically, we did a test there with the University of Wageningen and looked at the impact of flowers being pre-cooled. So all the field heat was removed and they were transported at 6 degrees, which is the lower part where there's an arrow with pre-cooled. And there was transport where the flowers got off the field and were transported in a refrigerated truck. And what you can see that are the two middle ones, that if you pre-cool and then transport without cooling, the average temperature during the transport stayed lower than that you put it in a regular cooling truck. What this meant is that the flowers, when they arrived at the destination, were better when they were pre-cooled and not transported cool, while the flowers which were not pre-cooled and were transported in a cold truck were actually worse off arriving there. Of course, it's best to do pre-cooling and cooling, but this shows the impact of removing field heat from the product, because that means that as soon as the product comes from the field, it starts deteriorating, and you slow down the deterioration as soon as possible by applying pre-cooling. So this is why it's so important and shows the impact of pre-cooling compared to cooling in more storage and transport ways. This of course comes with some conditions. If you get products from the field, it can be a lot of field heat. If a product is 20 degrees or 30 degrees, it has huge impacts on the need for cooling and the energy needed. And that will be addressed later in the presentation by Jeremy as well. So recognizing the importance of pre-cooling, then the next question is, when is pre-cooling needed? And we made a kind of graphical picture about that and showed in red and blue where cooling is needed, or in red where it's not. And basically, from a post-harvest perspective, pre-cooling and cooling is always needed. However, there's a limiting factor, which is economics. Because, for example, if you have a banana and you pick it from the tree in green, it can be easily brought to local and regional markets without the need for cooling. This is because it matures automatically over time. The same applies for mangoes, but also for tomatoes, for example. So that is why for the red top, you see that for local and regional markets, actually hardly any cooling is needed from an economical perspective for fruits which ripen after harvest. However, you see that the economical viability and technical need is high for products, for example, as fresh herbs and, for example, cabbage, which are low in the right corner. So important to recognize here is that pre-cooling might be needed from a technical perspective, actually always. But economically, there are limiting factors, and that's highly depending on the product market combination. And that's shown in this overview. And when we want to apply pre-cooling, then we have to know how soon we have to do that. And here in the guide, we provide an overview of different kind of crops, such as broccoli, spinach, but also oranges and pomegranates, and the acceptable hours of delay until the cooling is applied. This means that, for example, for broccoli, cooling needs to be applied within 4 hours after harvest to make sure that the water and firmness of the product is being secured. But if we look, for example, at grapefruit, which is on the right bottom, it only takes 24 hours, or the recommended or the acceptable delay is 24 hours. This has huge implications also on your supply chain design. For example, for broccoli, you would see much more decentralized cooling next to farms, while for grapes, you can work with bigger aggregation centers where products are coming together. And of course, like I said before, all these figures are depending on product market combinations, but these are general guidelines to follow. Let me go to the next slide. Yes, there we go. And if we are able to store the products on their optimal conditions, so with temperature and relative humidity being controlled, then the shelf life of products can be increased quite significantly. In the guide, we also provide an overview of the products which can be stored, such as the banana on top. And if you store it on an optimal temperature between 13 and 15 degrees and with a relative humidity around 90%, it can be stored between 1 and 4 weeks. If we look at, for example, potatoes, they are on the list, they can be stored for example, half a year when they are handled in a correct way. The same for onions, which is on the lower part. You see also that there is difference between dry bulb onions and green onions. The green onions only being able to be stored 1 to 4 weeks, while the dried bulbs are able to be stored for 4 or 42 weeks. And you also see the range of temperatures differ per product. So the guide provides this guidance on the optimal storage conditions to be achieved, but also the recommendations on the time the product has to be cooled to their optimal temperature. A couple of considerations for the cooling and pre-cooling. That is that we recommend also in the guide to harvest early morning. The reason for that is that the products are then naturally more cool, and that means that the heat load in the value chain will be lower. So first of all, it has benefit for the product itself because it's on a lower temperature, so it will decay less quickly. And moreover, you need less energy in the supply chain to reduce the temperature even further. Recommendation 2 and 4 are to keep separate rooms for pre-cooling and the already cooled products. You don't want to have influence of the products which are already cooled and not cooled in one room. So often in practice, we would separate the pre-cooling where the feed heat is removed and the storage. Also to prevent that, for example, the products which are already at temperature are overcooled or lose extra water because of the extra airflow. And that is also the third recommendation. That is more about ensuring that the airflow around the product is well. If you want to do pre-cooling, then you want to make sure that a lot of air is flowing past the product and taking away the heat. And if products are overfilled in crates, for example, then this prevents it from having that airflow needed to remove the heat. So that is why we give recommendations in the practitioner's guide to when considering to install pre-cooling and cooling. Oh, I made nice pictures, I thought, but here's the slide where I showed it in nicer pictures instead of in bullet points. So early harvest, make separate rooms for pre-cooling and cooled products, and airflow prevent overfilling. Then a recap I would like to do before handing over is that, first of all, know that products are alive, and you need to treat products which are alive as they want, like we want to be treated. So make sure they are at the comfortable temperature which they like, that they get the relative humidity in which they don't lose too much water or other, and in that way we can extend their shelf life. Then second recap is cooling and pre-cooling is technically always needed from a post-harvest perspective, but can be economically somehow challenging. So always make that consideration, and Giovanni mentioned that as well, like making considerations about the business model. So this is the second recommendation on looking into both the technical and economical need of cooling and pre-cooling in value chains. And with that, I would like to hand over to the next speaker.
Thank you very much, Bas. Okay, so hello from me. I'm Jeremy Tate. Welcome to everybody that's joined us. Thank you for taking the time to listen. So one of the motivators, one of the things that inspired us to start preparing this practitioner's guide was being aware of how many of the cooling plants and cold rooms that we were seeing, well, that colleagues and those working in these countries were seeing, the number of failed installations. And we did quite a bit of research, and the team, Baz's team at Wageningen, has done a lot of research looking at why these plants failed. One of the big issues was having equipment that was either too small to do the job, too underpowered, it didn't have enough cooling capacity, or alternatively, even plant that was simply oversized. It had too much capacity, it was too expensive to run, or demanded too much power, which simply wasn't available from the whatever power source was being used at the site. So we've got the challenge, and we're going to try and mention today some of the issues to help people put a number on the cooling capacity that's needed to do the job that you need doing. It's an important topic. It's quite a big topic. We certainly can't cover all the detail of it, but I wanted to cover 3 key things in the sort of next 10, 15 minutes or so. I'm okay staying on the first slide for now. Just while I mention these three things. Firstly, I want to talk about the concept of the design day, which you'll see on the slide in front of you. Secondly, I want to talk a bit about the overview. Don't advance the slides anymore. I'll catch up with that in a second. The second point was an overview of how to put some numbers on the heat flow, on the cooling demand, and thirdly, how to put some numbers on the airflow. This is the very important thing that Baz mentioned just now as well, as being something else which has to be present along with cooling capacity. You need to have that airflow, and there are ways of putting some numbers on that so you get plant that does the job. Now, it's a complicated and messy business trying to put a number on the cooling demand for a cold room, because it goes up and down so much. It's going to depend on the amount of produce you're loading in on that day. It's going to depend on the temperature of that produce, whether it's very hot from field heat. If you aren't able to pre-cool it before it goes into the store, then there'll be a big heat load coming in. It's going to vary according to the ambient temperature, which of course goes up and down during the day. It's going to depend on the design of the plant. It's going to depend how the management of the store is done. If the managers are really keeping control of keeping produce in the shade before it's loaded into the store. It's going to depend on how many people are using it, how they're going in and out, if the door's staying open, what the storage set point is, and indeed, given, as Baz has said, that this produce is alive, the amount of heat that it generates from respiration, the amount of humidity that it emits will vary depending on what type of produce is. And of course, the manager may have future plans for expansion, and you might want to think about that at the beginning. So it's a messy business, but we do have to put some numbers on it. And a suggestion we make in the guide is to think about having a design day, the basis of which you will size the plant based on the factors that I'll talk about just now. So if you go to the next slide to add the description here, the design day is in the indicative level that you might want to choose for sizing the plant. It's the basis of discussion with suppliers, or discussion between the supplier and the user or the specifier, and it's going to be a compromise. You're not going to have a very clear picture of this necessarily. It's a compromise between plant that's big enough to do the job and plant that's too expensive to be afforded. You can probably make some estimates of what a typical day might be. Hopefully you'll be able to make some estimates of what a peak cooling demand might be on the hottest day with the biggest amount of produce going through. And you can think about using thermal storage to try and offset some of that peak. But basically, you need to make a decision that's somewhere between the typical day and the peak day. On the next slide, we tried to put this concept into a fairly simple chart. If you think about the bottom of the chart, increasing cooling capacity, basically the payback period, or the total costs, if you like, if you get the plant too small, you've got missed opportunities for the business. It's going to become inadequate to do the job, so you've got opportunity costs there. If it's oversized, it's also going to become too expensive to run. It's going to become less efficient to run for most of the time. So next slide. You want to get some idea of where the minimum and the maximum might be, some idea of the average, and you're going to want to choose a design day setting somewhere around between the average and the peak. And the next slide, please. And this is going to be your decision. You've got to make some sort of compromise here, but you do need to have a decent idea of what your load might be to have plant that's going to be able to do the job. So on the next slide, please. In the guide, there's quite a substantial section that leads you through the process of estimating what that heat load might be. There's a whole section that describes the different heat loads that occur. They're summarized on this diagram here, ranging from the solar radiation on the outside of the unit, which will increase the heat transfer through the insulation. You've got heat coming in from the produce, of course, especially if it is warm from the field. You've got energy from fans, from lighting, all of which ends up as heat. And you've got people going in and out, which will bring heat and humidity with them. And there may be heating to make sure the door seals don't freeze. All of these things increase the heat load. And within the guide, there are options given for how to put some numbers on these. There are equations that you can use to calculate based on properties of each of these, the types of equipment that we're talking about. There are links to online models, which are some of which are produced by suppliers of equipment, some of which are supplied by technical institutes. Those can be used to enter the details of your particular configuration. They will help you to estimate the heat loads. And there are also calculation tools available to download that can help you through this process. But it's a good idea to start simple. On the next slide, you can perhaps start with simply looking at what the heat load is through the transmission. And there's an equation to help you do that. If you know the area of the insulation around the cold room, you know the thickness and the type of insulation. The formulas are given to help you calculate the actual heat load that comes through. And if you can make that relatively simple calculation, you can then look at what capacity in your plant is left over for dealing with everything else. And you can start to get a feel for just how feasible it is. And Victor will be talking you through an example of this in a moment, which I think will be helpful to understand the process and some more of the thinking that needs to go into this. So you don't have to go through all the maths yourself, but if you familiarize yourself with the contents of the guide and the issues that are flagged in there, you can then have a relatively detailed conversation with suppliers or experts or people that you can discuss these things with to help each other through the process of getting a plant that's actually up to the job. You basically need to find people that you can trust to discuss, to advise you on what types of plant, what capacities of plant are going to be needed to do the job. We can also, in the guide, give some benchmarks for what sort of capacities you might expect. And on the next slide, we can show some benchmarks that have been pointed out by our friends at the Post-Harvest Education Foundation. There's a number of the papers published by them that are referenced in the guide. And this particular table gives some indicative cooling capacities that have been found by experience to be able to cope with the demands of a certain situations. These vary depending on the square meterage of the cold room, of course, and how much is in it. There are ranges given for a store at around 1 degree centigrade and around 13. And that range that you see there in terms of the necessary capacity shows between the capacity you'd need in a moderate climate, and at the upper range is what you'd need if in a lowland tropic or semi-arid region. So those might be helpful in giving some confidence that the capacity of kit that you're considering or are being offered should be able to do the job that's needed. So having adequate cooling capacity is not enough, as Baz has already pointed out, and we really need to put some numbers on the airflow that you'd need as well. So on the next slide, you might remember seeing this particular diagram that Baz showed earlier. So this is showing produce stored inside a cold room and particularly focused on the airflow that's being forced through the produce. Now, when trying to put some numbers on this, fans, evaporators, or systems that use thermal storage should have a figure given for the cubic meters of airflow that they achieve per hour through the cooling fins or through the thermal storage. And that can help you understand what you're going to achieve inside the room. On the next slide. And through research on what benchmarks are commonly in use in Europe, and indeed also we found very similar benchmarks in the Indian advice, the Indian government advice. If you look at the airflow achieved by the equipment, by the fans, and divide that by the volume of storage you have in your room, you get this ratio, which is called the air changes per hour. And good practice for Europe generally suggests that you need a figure of around 50 air changes per hour if you're just looking at storage. If you want to achieve pre-cooling, you're going to need at least double that number of air changes, basically. 120 is a figure that seems to tally with good practice advice for Europe and also in the Indian government advice. And it was quite surprising when we found that these sorts of numbers were not being discussed by many other suppliers of equipment in this market. And we want to generate a bit more discussion around that. We're looking to find out what sort of benchmarks are possible and in use in these sort of global south markets. And I'll mention at the very end some work that we're doing to try and move that forward. So this topic of airflow is discussed in several parts of the guide and is well worth checking to make sure that your investment in cooling capacity is actually impacting the quality of the produce as well by having adequate airflow. And the last stage of the slides I was going to mention today on the next slide is just where you're putting together the turning that cooling demand into an electrical power demand, which you then can consider in the electrical system specification. So if you're simply using a monoblock sort of through the wall unit, then there will be a electrical power demand quoted based on its cooling capacity. If it's a bespoke system with lots of components, you can look up the figures from each of the components, particularly thinking of compressor and whatever's using fans because they're high power units. That can be added together, and together with, on the next slide, the next list there, all the other electrical loads that together make the basis of a design day for electrical demand. And judgments have to be made on what's the typical, what's the highest likely demand for each of these uses for power. And together, adding them together, you'll get a decent feel for what sort of total electrical demand you're going to need. And that is what is handed on to the electrical system specification. And Victor will pick up that theme, as well as recapping some of these other aspects that I've mentioned, to think about the specification of a system for powering the unit. So I'll hand over to Victor. If he's standing ready, please pick up that. And anything else that you want to add to what I've already said, please do.
Thank you very much, Jeremy. And hello and welcome also from my side. My name is Victor Torres, and I'm very happy to drive you through an example so that we can see figures on the design process of a typical cold room. So if we go for the next slide, I would like to review the design process again for you. So the first step is, as Jeremy just mentioned, is to analyze the heat load, the heat demand of the cold room, which is based on different aspects, as you see here, mentioned in 9 different steps, which are very well described with the equations in section 4 of the guide. The most important here is to analyze, of course, the thermal losses through the walls, the air infiltration, and then, which is very important also, is the amount of products that you are introducing into the cold rooms. If you are having pre-cooling, depending if you have separated rooms for storage the products and pre-cooling the products. The next steps, and is the one I would like to focus in my next slides, is how to convert this cooling demand into electrical power. And this is a very exciting process because the cooling demand is in thermal energy, and then you need to convert that into electrical energy, and this is done by a cooling system, of course. So we are talking here about vapor compression heat pumps that are able to pump the heat from the inside of the cold room to the outside with a certain efficiency. And this efficiency is described through the coefficient of performance, COP, and this also depends on the ambient temperature and depends also on the cold room temperature. So you see the ambient temperature is affecting us in the thermal losses, but also affecting the coefficient of performance of the cooling unit. So as you can imagine, cold rooms, the energy consumption is very affected in overall by the ambient temperature. Once you have this, there is the next step to decide on the power supply, and this depends a lot on the grid, how available it is. So in the guide, they are very well defined how the grid is described based on the availability of it. And on top of this, you can consider, of course, using solar or solar with batteries, electrical batteries, or with thermal storage for the cold room, as is described here in this next step. So I would like to go to the next slide and go a little bit more in detail. As I mentioned in the section 4 of the guide, there are all equations described how to calculate the cooling demand. And in the section 5, there are some examples, as the one I'm presenting you here in table 5.6, where we have a typical 20 feet container size walk-in cold room with a 100 millimeter polyurethane insulation, so typical sandwich panels. The cold room temperature is 2 degrees, and we are willing to design this cold room for a maximum ambient temperature of 35 degrees. And here I come back to the concept introduced by Jeremy on the design day. Yes, you need to take a design day as an average of what you are willing to design, which is based on a typical climate day and also a typical cooling scenario with a certain amount of products. In this table, you can find all details of the cold room that has been analyzed, and here you see the heat loads. So this is the calculation of the cooling demand divided in the different factors that are considered. So the transmission losses, this is the thermal loss through the walls, air infiltration, respiration, and so on. And we are coming here to maximum, I would say, a cooling demand of 1,900 watts. And this is what we are going to take as a reference for our calculation. So if we go for the next slide, please. We'll have a look here to first, before we start calculating more, we need to decide which kind of cooling system we are taking. It, of course, make a difference if we are having a cooling system with thermal storage or without thermal storage. The most typically used cooling systems are the ones described here in this figure. So you have from the one side, here on the left, you have monoblocks cooling units that are, as you can see here, is a cooling system that is integrated in the sandwich panel. So you just have a hole in the sandwich panels, you install the cooling system there. As you see here, they are called monoblocks, and then there are the other systems that are a split type. It means you have the condensing unit outside, as you can see here, and the evaporator inside. Both cooling systems have the same working principle. So they are just the way how they're built are different. And for the power supply, we are going to consider to run our monoblock with the grid, but also considering the use of PV panels, which are then made available for the monoblock through an inverter, and as option also using electrical batteries. So the questions we have now is which monoblock type do we need? So how can we select this from the different suppliers that are available? The second question that we'd like to answer is what is the size of the solar system that would match the energy demand of our monoblock? And then we'll like to make to solve the question if we should use electrical batteries and if we should consider thermal storage also for this cold room. So in the next slide, we are going to select the monoblock type that we want to use. So I'm just showing here a typical datasheet of monoblocks. So we'll find here different models, so depending on the compressor side. Then we see there the compressor input power, and then we normally find the cooling capacity. So which is the maximum cooling energy that the monoblock can provide. And this is based to the cold room temperature. So depending on the set point that we have for that monoblock, we will see here different values for 0 degrees, here 5 degrees and 10 degrees. So this is given in watts. So in our case, we need 1,900 watts for our cold room in the worst case scenario when the ambient temperature is 35 degrees. By the way, the manufacturers also provide the cooling capacity based on an ambient temperature. This is also important to consider. If the ambient temperature is low, then the cooling capacity will be higher, as we are going to see in a minute. Next slide, please. So now we are selecting based on that the Model 3, which provides a cooling capacity of 1,900 watts. At 2 degrees, this is what we need. And if we divide this cooling capacity by the compressor input power, we get our COP. So this is the coefficient of performance that we can expect for 2 degrees cold room temperature and 25 degrees ambient temperature. So this COP is what is giving us the relationship between thermal energy, cooling demand, and electrical power. Next slide, please. But what is happening during the day, the ambient temperature will be changing, right? So if you consider here in this graph, the ambient temperature, so it goes from the 22 degrees to up to 35 degrees and then going down again. The COP will be 2 when the maximum temperature is at highest, 35 degrees, but then it will go up to 3 at night. So we will have less energy consumption at night than during the day. So in the next slide, I would like to drive you through the typical cooling demand profile that you will find. So this is what you see here. This is the cooling demand. So you see here we have the maximum value of 1900 watts, and then divided by the COP that is also changing based on the ambient temperature, you get a profile for your energy consumption. So this is the electrical power that you are consuming. So you see it goes from 500 watts to 1000 watts. So the duty cycle of our compressor will be around 74%. It means it will be working 74% of the time. Now we are willing to calculate a suitable solar system for this. So at the moment we have already the energy consumption all over the day for our design day with the maximum and minimum power. Next slide, please. Here, now we are going to consider what is the PV panel size that we will need for a scenario with the grid and with solar. So we are connected to the grid, but we want to run also on solar with a hybrid inverter. So as you can see here in green, this is the electrical power profile. And here in yellow, you see the solar energy provided by PV panels of 3.5 kilowatt peak. So the area that you see here is all provided by solar. And this is around 45% of the overall daily energy consumption for the cold room. So you see with only solar, you can already cover a high portion of the energy demand, and the rest at night you can cover by the grid. Next slide, please. Here you have a scenario as a solar off-grid. In this case, we not only have solar, we have also electrical batteries. So you see the energy provided by the PV panels has to be higher so that it can cover the energy provided by the energy needed for the monoblock. So you see here the solar power. This energy here is provided directly by solar, and this energy is provided by the batteries. So we are designing here a 12 kilowatt hour battery useful energy so that we can run the cycle and have in overall 100% energy savings through such a solar system. Next slide, please. So the recap of the considerations for the design is to make sure that the coefficient of performance is well analyzed. You need to get this from the manufacturer. The COP gives us the relationship between heat demand and energy consumption, and it is only valid for a given ambient temperature and a cold room temperature. So if the ambient temperature is changing because you are designing for another location, or you are having another cold room temperature because you have another product inside, then the COP will also change. Up to 50% of the energy consumption can be covered directly by solar. So without batteries, this is very interesting, and this is the ideal configuration for reliable grids. In most countries of the world, solar is cheaper than the grid electricity. So this is a recommendation for reliable grids. If you are having unreliable grids, then you will need to consider electrical batteries, which are also, in most cases, much more cost efficient than gensets. Thermal storage is not only a way to substitute electrical batteries, but also serves as a buffer of thermal energy for high pre-cooling scenarios, high power pre-cooling scenarios. This is described in the section 5 of the guide. And to take the decision on that, if you want to have a big compressor, so a big monoblock, or want to have thermal storage, for this you need to do a cost-benefit analysis where you then do the design for different configurations and analyze the cost of both. So that's all from my side. I thank you very much for your attention.
Yes, so thank you very much for all four of our speakers. Now we have a time for questions and answers on challenges that might be faced by designers and buyers. Thank you for the participants that have been using the Q&A section so far. Don't hesitate to continue to post your questions. Some of the questions have already been answered by our speakers, but I see a few ones that haven't been answered. So I'm going to read a question. How do we know power consumption for each size of cold room? Or anyone knows about technical standard for energy consumption cold room?
Well, maybe I can give an answer to the first one. When you go to the electrical power need, as you have seen in the presentation by Victor, the electrical power consumption is depending a lot not only on the size of the cold room, on the way it's operated, say for example, how much warm food has been loaded, but the ratio between the cooling capacity and the electrical power, which is the coefficient of performance, strictly depends on the weather conditions, on the outdoor conditions. So it's quite difficult to give a figure. It depends a lot on the way the system is operated and the electric and the cooling system is operated. Anyway, through the calculations that Victor showed in the tables, you can estimate the coefficient performance at different outdoor temperature, and so you can try to find out an energy use. And it's also very important to take care of maintenance of the system. There's a condensing unit in the system to release heat outdoors, and it's very important to keep it clear. Otherwise, the condensing temperature, which is the temperature at which the system will reject heat, will increase, and this leads to a poorer coefficient of performance. So not only a good design is needed, but also a good maintenance is needed to keep the electrical power at a low level. I don't remember the first question. The second question was about the simulation tools, if I'm not wrong.
Yes, let me read to you the second part of the question. So the second part was,
yes.
Does anyone know about technical standard for energy consumption cold room?
No, I don't know. I don't know if some other.
Okay. Well, I could perhaps pick up an answer to that. I don't know if it's quite what the questioner was after, but yeah, there are a number of international test standards that relate to the consumption and heat demands for cold stores. I'm thinking in particular of the European standards that set out how to calculate the heat load through the insulated enclosure of a cold room. Those are all referenced in the guide. There's a big reference section at the back. Yes, actually, there is a section in the references that specifically addresses technical standards, international standards. So that's going to be worth a look at, I think, for you. And there are a number of good practice guides for cold room design, including very substantial guides published by the UK Institute of Refrigeration, by the International Institute of Refrigeration, and by the Australian Air Conditioning and HVAC Association has also published a very good guide on small cold room energy efficiency. DA12 is that, and you'll find these referenced in the guide. And indeed, there's a slide at the very end of today, which I've listed a few of these on. So yeah, lots of sources are out there.
Thank you very much. So I'm going to read another question from Caesar. How to combine the design of thermal energy storage systems with the sizing of batteries?
Big topic. I don't know if Victor can respond to that one, maybe.
Yes. Victor, would you like to give an answer? Otherwise, I can try.
Yes, I can also kindly try to give an answer for this, Giovanni, and then you can add. So normally the best way is to design the systems from the beginning based on a configuration. So we cannot design a cold room and then say, okay, now I'm going to substitute the electrical batteries by the thermal storage, because there are bigger implications in the process. So for example, a thermal storage system normally has a bigger compressor, so a bigger cooling capacity, because it has to provide the cooling demand within the solar radiation hours, right? So it has only 6 to 7 hours to provide the cooling demand. So you have a bigger compressor. Then the compressor is operating when the ambient temperature is higher. So the COP also is lower, and it has to cool down also to a lower temperature, because you are storing the energy into ice or a phase change material. So the COP is also affected. It means the electrical demand will be also different for electrical batteries and thermal storage. In this case, if you follow the process for both configurations, so you figure out, for example, for the electrical batteries, in the same way we have done it, you select the monoblock, you select the solar system and the electrical batteries, inverter, and so on, then you have the total cost of your cold room. Then you do the same for the thermal storage. You consider a cooling system that is able to store the energy in thermal energy during the day with the thermal storage, which can be, for example, an ice bank and so on. Then you normally have a secondary circuit that transport the energy of the ice bank inside the cold room. So this has also a certain energy consumption and a cost. And then you have designed the system like this, and you can compare the cost of both systems. And then based on that and on the expected performance, you can decide to go for one or for the other. But there is no way to say, I substitute, for example, 10 kilowatt hour electrical batteries by 10 kilowatt hour thermal storage capacity. So there is not compatible to do it like this, because of what I mentioned. The COP profile will be different for both systems, and that's why you need to do the design from the beginning for both estimations. What I can say is the cooling demand will be the same for both, right? So the cooling demand is the same, and then it's only the electrical, how you provide that cooling demand is different with electrical batteries and thermal storage. I hope that's clear, and please, Giovanni, add your comments too.
Oh, very clear, Vito. Thank you. And I will just add a couple of things. The first one is also an answer to another question, and it's related to startup current of the compressor. So maybe a battery is in any case needed to allow the system to start, the compressor to start. Otherwise, if we only rely on solar modules, we cannot start up the compressor. And the second point is about reliability in time. So maybe batteries every, say, 5-6 years, I don't know exactly, will need to be replaced, with the cost and the problem of how to deal with the exhausted batteries. Otherwise, a phase change system maybe will have the same lifetime as the system at the cooling plant. So this is also another question, another topic to be considered, to find it exactly the trade-off.
Okay, thank you very much, Giovanni and Victor. I read another question. Is it necessary for refrigeration equipment, specifically compressors, to be a variable speed to operate with solar energy systems?
Victor, I think it's yours.
Yes, thank you. It is very recommendable for something that Giovanni just said. The start current of the compressors is a factor. So if you are running a compressor on solar, and you can have a compressor that runs on variable speed with inverter technology, then the start current is much softer. So you can run on a soft start, then the compressor can adapt to the cooling demand. So which is also efficient. And this is very kind for the inverters, because then the inverter doesn't need to be oversized. It can be quite close to the nominal power, and this saves you also money. So it makes your life less complicated for the design of the inverter. You save money in the inverter, and it's also more efficient. So yes, very recommendable for solar power cold rooms.
Thank you very much. Another question is, someone asking about a technical challenge in startup current in compressor, which is higher up in their case of 32 ampere.
Yes.
Which will be the solution?
It has been already answered,
Okay.
Monique,
Okay.
I assume. Yeah.
Okay, sorry.
No worries, no worries.
I had also a question concerning electrical versus thermal energy storage. Which of these options is the most financially sustainable solution?
Who knows? It depends on a lot of things. Vitor already listed a lot of variables, and all of them have a cost. And on the other side, I also added the problem of reliability with time and the need to replace the system, the batteries every, say, I would say, for example, 6 years, 5 years. So otherwise their capacity will reduce a lot. So it's not so easy to find financially the trade-off and the exact solution, the best solution. It depends a lot on the application, actually.
I mean, one of the bodies that we've used, relied on for advice, technical advice, in the production of this guidance is the WHO, and their program of developing specifications for freezer and cooling equipment used in healthcare for vaccines, etc. And one of the key learning points that their experts really pressed upon us was that in the field, once the kit's been out there for 5 or 6 years, as Giovanni mentions, getting batteries changed, finding the right battery to swap out, getting hold of the batteries out in the field can be really quite challenging. And the technical teams on the healthcare side are really quite determined to reduce reliance on batteries as much as electrical batteries as much as possible. They're really trying to work out the very best ways to use thermal storage and design their systems to make sure they're capable of charging those thermal stores to get them through periods of low power and peaks in demand as well. And if your thermal storage can be based on ice, simple ice, water in containers or ice banks, that's a very easy to replace way of storing energy, and is something that I know Victor and your teams have done a lot of work on. But yeah, there are pros and cons for both. But Victor, do you want to expand on any of that at all?
Yes, I think you have mentioned already everything. What I would like to say also, it depends a lot if you are connected to the grid or not. So if you can be connected to the grid, you know, there, for example, when you have these fluctuations on energy, so there are days you have more products in the cold room, there are days that are very hot. And if these fluctuations can be covered by the grid, but you can also have solar and so on, then the combination solar, grid, and perhaps small batteries is very, very economical, cost efficient. But if you have a solar off-grid system without the grid, then is where the thermal storage plays an important role for the things that has been mentioned, reliability of batteries, and also to be balancing the fluctuations on solar. For this, I like thermal storage a lot, because the thermal storage never totally stops, right? When the batteries are over, so they have achieved the minimum SOC, they really stop the compressor. This means the products will start to get hot and so on. A thermal storage never totally stops of working, so it just increases the temperature slowly, and this gives solar off-grid systems more makes it more robust, so to say, against solar fluctuations, the batteries getting old and so on. Yeah, that's why I prefer that, and they make the system be on the overall lifespan of the system to be more cost efficient. But I have to say also, not every system is compatible with thermal storage, so it depends also on the temperature. When the temperature of the cold room needs to be very low, then you have to use phase change materials and so on. Then the cost of thermal storage gets higher. When you can use ice banks, for example, the cost efficiency is normally better. So as you have seen, there are many different factors to consider. Mm-hmm.
Thank you very much. We still have a few minutes left. I think, Jeremy, perhaps you would like to share on the further resources. I think even you mentioned that some of them may be a complement to an answer to the question. So
Exactly. Yes, thank you, Monique. Yeah, so I wanted to just alert the listeners to some parallel activities that are going on that may be of interest to you. So firstly, the Verasol scheme is mentioned on the next slide. This is a product certification scheme for off-grid equipment, and building on their existing certification schemes, they are very keen to develop some sort of quality framework for walk-in cold rooms. They want to be able to help programs and buyers and suppliers to assess suitability of this type of equipment, and very much aligned with the sort of equipment we've been talking about today, and really very much also trying to help to work with the suppliers themselves to help develop good benchmarks and the technical basis for performance assessment so that better products can be made available. The Verasol scheme, you can see the website there if you want to find out more, if you're not familiar yet. But on the next slide, I'll just flag quickly the process that's going on for developing this quality framework. It's something that myself, I'm involved in, working with an excellent team to take this forwards. And there's been a study of existing quality frameworks for cold rooms that's been completed now. We've created a test method expert group, which is considering how the equipment would be tested if it was to be tested in a thermal chamber. And we're also running an interest group open to anybody who would like to find out more and help and comment on the framework that's being developed. It's an ongoing process. We will be hopefully making available the first sort of public quality framework outputs towards the end of this year. If you want to get involved, then please drop us an email and we'd be very happy to let you know. We'll put you on our email list, and we'll keep you informed when the next meeting is coming up, and you can listen in and find out what's being proposed and comment on that yourselves and help influence what we develop. The next initiative I wanted to flag quickly is that the Global Off-Grid Lighting Alliance, the GOGLA team, have been publishing sales data to help understanding and encourage investment in this whole off-grid market. And they publish aggregated sales trend data. And they would really like to start looking at how the market for cold rooms is developing. They are inviting suppliers to help them by providing sales data. The data would remain completely confidential as far as the individual company is concerned, but they're working with the sector to develop the best ways to aggregate that and publish it in a way that's helpful to understanding what's going on in the market without compromising the interests of any particular suppliers. So please do get in touch with Sarah at GOGLA if you're interested to help that process. The third slide I had here was just a a few selected resources that are taken out of the guide. There are, I don't know, a couple of dozen links we've included to very good reference sources on different topics. I'd also flag that the more we're discovering about the excellent material published by the Indian government and by NCCD and other bodies in India about these topics, it's really some really very valuable information being published by them, very practical and great insights on design and good practice. We flagged several others on this slide. The slides will be made available to you, and there's a lot more in the guide itself as well. That's all I really wanted to say on that. The guide contains a lot more links, and we will invite you to read up on many more topics, whatever ones are most important to you. I'm happy to hand back to Monique.
Okay.
Yeah.
Thank you very much, Jeremy. I think there are no more questions. No. So thank you
No.
to all
Just-
our speakers. Yes.
Just a line to conclude, Monique. Then I will hand over to you. And one suggestion: if you, for the best use of your money, please take care of two things which are very important from our point of view. First one, the cold room is not always the best solution. Maybe you can also need something different to enlarge your harvest season or whatever. So please take care to choose the best solution, which is not always the cold room. And second, please remember the speech by Bas at the shed. Pre-cooling is very important. It takes another plant, another system, differently sized. So it's very important that the two things are considered differently, cold storage and pre-cooling. I think it's been one of the most important things we wanted to stress when writing the guide. So I want to stress them also in this occasion. Thank you, Monique.
Yes, I see
If I-
Jeremy would like to
Yeah,
add.
Yes, please.
if I could just extend the invitation to all those who are listening, please, to help us to work together to establish some reliable benchmarks, rules of thumb to help steer people through this rather complicated and quite tricky field of deciding what plant is right for them. I think that the more we can gather together in terms of evidence of what types of plant are working well, what capacities, what choices of design are working well. We're very keen to put some numbers on this and and then publish and share those benchmarks back to the market through that quality framework and through other guidance that will be published by our team and others, we hope. So yeah, please, if you've got good examples of system designs that have been tried and tested, if you're happy to share that, we'd be very pleased to build up a better picture of what sort of kit is working well and what numbers of capacity, putting some numbers on to help people through this rather tricky process of decision making. So yeah, it's an invitation to speak up, get involved, help the market develop. So thank you in advance for that.
Thank you, Jeremy. I see that we still have a couple more minutes, and I see last minute comments. I don't know if that was covered already. Someone asks if we've covered the question of refrigerants.
Yes, in the guide we do talk about that rather thorny topic. So yeah, there's a section in there about environmental considerations generally, and particularly on refrigerant choices. We've tried to point people towards the best resources on that and advise on what should be a practical solution for you to ensure that the impact of refrigerant choices is really minimized. So I'd refer you to the guide.
Okay, thank you, Jeremy. I'm checking the chat section and the Q&A section. I think that all questions have been answered. Yes, so thank you once again, Giovanni, Victor, Jeremy, and Baz. Thank you very much for your very interesting presentations. Once again, the Practitioner's Technical Guide is available for download freely on the IIR website, as well as on the Efficiency for Access website. This presentation has been recorded, and the recording will be made available on our YouTube channel, and the presentation will be available on the IIR website shortly. So thank you very much. Bye,
Thank you,
everyone.
everybody.